Hello, everyone. So I'm Manibrata, a postdoc with the NGS network at UC Berkeley. And today I'll be talking to you about a model of sterile neutrino dark matter and how one can use the concept of extra radiation in the early universe to probe these kind of models with upcoming cosmology experiments. So this talk is based on these couple of papers which are published in PRL in the last 1 year or so. And since this is a recorded talk, if you have any questions, we can discuss more in the discussion session. So let's get started. So what is the sterile neutrino? A sterile neutrino essentially is an additional single standard model singlet fermion, which basically, as the name suggests, does not interact with almost the entire of the standard model. Why do we want such a candidate? So firstly and first and foremost, we have a theoretical bias. We are theorists, we like to introduce new particles. And as a result, any new particle that we can introduce to solve an experimental anomaly is always welcome. Are there any experimental anomalies? So it so turns out that in the field of neutrino physics, there are a number of anomalies, both from terrestrial experiments as well as from cosmology experiments, which basically can be solved if one postulates the presence of these new sterile neutrinos. So you have these short baseline anomalies, reactor anomalies, and then cosmology value of ineffective, and all these suggest that maybe the three neutrinos that we know about are not the only one in the universe. So let's say along with these three neutrinos, which we know how they look like, we have these additional sterile neutrino, which we don't know what it is. So why is the sterile neutrino such an attractive candidate? Firstly, the sterile neutrino, as the name, as I say out here, it provides the standard model with the right partner. Essentially, it's just the right-handed, it can be the right-handed component of your active neutrino field. And hence, this can be a very useful means to give masses to neutrinos. Secondly, it can also be used to answer the long-standing question of the baryon asymmetry of the universe. It gives you a good solution for that. Of course, it's a possible dark matter candidate. So that is what is going to be the major theme of this talk. And again, as I said, there are hints in terrestrial experiments. So with that kind of an introduction, let us start getting more and more deep into the model to see what kind of sterile neutrinos are we talking about. So in this talk, when I talk about a sterile neutrino, I essentially refer to a fourth mass eigenstate, which essentially is a linear combination of the sterile state and the active state with some mixing angle theta. Now, once you postulate the presence of these states, you can immediately detect these states by a decay through a one loop process. So essentially you can have a sterile neutrino oscillating into an active neutrino, and then this can decay into an active neutrino and a photon. So if you can detect these photons, so typically if you are in, let's say, if you're interested in keV scale sterile neutrinos, these photons would be X-rays, then you can immediately try to probe these models. These decay rates essentially depends on the mass of the sterile and its mixing angle. So on the contrary, if you do not detect these X-rays, you can actually put a bound on these parameters. So the question is, have we still been able to detect any such X-rays or not? So the dust on this matter has not yet settled. There have been claims from certain experimental groups that they have seen a radiative X-ray line exactly at 3.5 keV, which can be explained by the decay of a 7.1 keV sterile neutrino. However, there are groups that claim that this this line cannot be attributed to the decay of a sterile neutrino, and think, in my opinion, this matter is still a matter of active research and the dust on it has not yet settled. But let's say there are these sterile neutrinos, irrespective of whether this line is due to sterile neutrinos or not. And then the question that we want to ask is that how do we produce these neutrinos? One thing is for certain, we cannot have these neutrinos very tightly coupled to the active neutrinos in the early universe, because if that happens, these neutrinos would be in thermal equilibrium with the standard model particles, and then you end up producing too many of them before, and thereby screwing Big Bang nucleosynthesis. So that is not allowed. So you have to produce them non-thermally. One simple way of producing them is through this Dodelson-Withrow mechanism, which was suggested in the early 90s by Dodelson and Withrow. And the idea is that you have these large amount of active neutrinos in the early universe. They have a tiny mixing angle with the sterile neutrinos, and these active neutrinos can oscillate into sterile neutrinos. But every once in a while, these active neutrinos essentially undergo weak interactions of this form. And what this does is it freezes the flavor content of this ensemble, thereby letting the resetting the flavor of the active neutrinos, whereas the sterile neutrinos don't really interact through weak interactions, so they can just free stream through. This gradually leads to a production of sterile neutrinos in the early universe, and this in principle can be used to explain the dark matter relic density of the universe. So mathematically, this can be explained by a semi-classical Boltzmann equation of this form, where the rate of production of sterile neutrinos essentially depends on three quantities: the distribution of active neutrinos in the early universe, the average probability of conversion from active to sterile, and the rate of producing these active neutrinos. This probability is essentially averaged over one mean free path. It depends on the mixing angle, which is typically very tiny. It depends on the interaction rate, which produces these active neutrinos, and it also depends on these matter potential. So this interaction rate is an interesting quantity. What it says is that if these sterile neutrinos interact too rapidly, these active neutrinos are produced too rapidly in the early universe, the flavor of that remains frozen, and essentially there is no conversion from active to sterile. This is this famous quantum zero regime. On the other hand, this potential essentially has two contributions. It has a finite temperature contribution, which is proportional to some powers of temperature, and it also has a finite density contribution, which is proportional essentially to the difference between the fermion number densities. These can be calculated by computing one loop diagrams of this form. So once you have this, you can in principle solve this equation and ask the question that what fraction of these sterile neutrinos form the relic dark matter relic density of the universe. And you can see that if you want to calculate that in the parameter space of the mixing angle, sine square of the mixing angle, and the mass of the sterile neutrino, you would have to lie on this black solid line. So if you lie on this black solid line, you can produce the correct amount of dark matter in the early universe. However, as I said, these sterile neutrinos can be detected by their decay to gamma rays. And if you do not observe these gamma rays, you can put constraints on this plane. So it turns out that non-observation of these gamma rays puts very tight constraints on this plane. It essentially rules out almost the entire part of the parameter space. This blue shaded region is the constraints that come from non-observation of these X-rays. And as you can see, the entire black line is covered by it. There are other constraints from phase space arguments that these sterile neutrinos are fermions and you cannot pack too many of them inside a certain volume. And this essentially, and even there are Lyman alpha arguments, which I have not shown out here. But the crux is that a combination of all these arguments can rule out this black line completely. So the vanilla dark matter scenario, due to the Dorilson-Wither mechanism, is currently in tension with astrophysical bounds. So the game is we have to push this line down to this white region where there are no constraints. And if we can introduce some new physics which can do that, then in principle, we can save this model. One very interesting suggestion was developed in the late 90s by Shi and Fuller, where they say that let's put in some extra lepton asymmetry in the early universe, and this can give rise to extra resonances, which in principle can push this line down to this region. The downside with this argument is that it requires lepton asymmetry to be reasonably large, and it's very difficult to constrain such lepton asymmetries. Then so the question is, can we avoid introducing a large lepton asymmetry and still make this model survive? This then we came up with this idea in last year, where we suggested that, okay, instead of introducing a large lepton asymmetry, let us say that the active neutrinos have some secret self interactions. So it's not unusual to expect that these neutrinos can have some secret self interactions, but let's just go to the regime where these self interactions are actually much stronger than this usual weak interactions, maybe a factor of 1,000 or even more stronger. So why do we want that? How does it help? So naively, if I want to calculate the rate of producing these sterile neutrinos, it goes as a product of two quantities. If you go back to these equations, it's basically the product of the rate of producing the active neutrinos in the early universe, and then some quantity which quantifies the conversion of these active neutrinos to sterile neutrinos, which essentially depends on the mixing angle. Now, if we want to save this line, we need to push it down to smaller and smaller mixing angles. The natural way to save this is to increase the rate of production of these active neutrinos. And this is what these secret self interactions can do. So if you have these secret self interactions, which are way stronger than the usual weak interactions, we can increase the rate, thereby allowing these neutrinos to be produced at the same amount at a much smaller mixing angle. And this in principle can allow us to push it below the X-ray bounds as well. Of course, there are constraints on these self-interactions. There are constraints from BBN. There are constraints from lab processes, essentially from meson decays. There are constraints from the decays of the Higgs and Z's. And all these decays are there, constraints are there. But it so turns out that if you are in the regime where the neutrinos interact pretty strongly, and if you, let's say, look for muon neutrinos or tau neutrinos, these constraints are less strong. And you can, in principle, open up a large region of parameter space where you can produce these dark matter candidates. And this is exactly what we show out here. So if you postulate these active neutrino self interactions, and let's say they're mediated by the scalar phi, then in principle, you can open up this entire region of parameter space in this in between these shaded regions. So for each value of this, each value in this parameter space in this white region corresponds to some combination of the coupling, self interaction coupling, and the scalar which mediates these self interactions. And for each of these things, you can in principle lie in any part of this parameter space and then can evade these blue x-ray bounds. This is the standard Dorelson-Widrow line which I had shown before, and you can lie anywhere out here. This allows you to produce these dark matter candidates very nicely without running afoul of these bounds. Of course, the question comes as to whether you can put more constraints on these interactions, basically constraints on this parameter space of lambda phi and m phi, and that will not be the topic of my talk. I encourage you to check Yue Zhang's talk in the dark matter panel, where he'll discuss more on this. Essentially, the idea is that the upcoming experiments like Dune can in principle probe some parts of this parameter space, and that would be interesting to look at. The thing that we want to focus out here is that as we look on this plot, if we want to put bounds on these parameter space, one region seems to be totally inaccessible to us, regions of masses of this scalar less than a few MeV. So the moment you end up producing these scalars with less than a few MeV, you run into the problem of BBN. You end up producing too many of them before Big Bang nucleosynthesis, thereby screwing up all your predictions of the primordial abundance of these elements. So the question is, that we want to address in the remaining part of the talk is that, is it possible to still have this scalar sub-MeV, let's say, much less than an MeV, and still get some region in the parameter space where we can produce these dark matter candidates. Additionally, of course, if we do have these scalars to be sub-MeV, there has to be some correlations with extra radiation that you produce in the early universe. And then can you use upcoming cosmological experiments to put additional constraints on this parameter space? So then let's say we operate in the sub-MeV phi mass region. So the scalar that mediates these self interactions are sub-MeV. And the question is, how do you evade these BBN bounds? The idea is very simple. We do not produce enough amount of phi's before BBN. We have to tune our problem such that there is negligible population of these phi candidates before BBN. And then we want these phi's to come into equilibrium with neutrinos only after BBN, when the neutrinos have also decoupled from the plasma. So what happens is that the neutrino and the phi system forms a tightly coupled closed system in itself, and this evolves over time. And just before CMB, we allow the phi to decay into a pair of neutrinos again, where one of these neutrinos can in principle oscillate into a sterile neutrino, and then this produces these dark matter candidates. Now this can be done more technically by solving the Boltzmann equation to see the amount of phi that you produce after BBN. And then you have to calculate the temperature of this phi new system, because now the neutrinos have decoupled from the plasma, so they don't share the photon temperature. Having the phi equilibrate with the neutrinos would change its temperature. You calculate what the temperature is by using energy lepton number conservation. Also in this, because this is now an isolated system, this develops a chemical potential of its own. You have to compute that by again using these conservation equations. And finally, once the phi decays to this pair of nu and nu s, you again have to use things like entropy conservation and lepton number conservation to again calculate these quantities, so that finally you can calculate what's the temperature of the decoupled neutrino sector, and that you can relate it with the delta N effective in these two particular areas, the BBN era and the CMB era. I can go into more details in the discussion session if you have more questions on how this computation is being done. So let's say we can do this, and we want to go back to this plane of the scalar coupling and the mass of the scalar. And these black lines essentially show you the regions where you again end up satisfying the entire dark matter relic density. So the first thing to see is that now we are in a sub-MeV regime of phi. So phi goes up from 1 keV to thousands of keV, which is essentially 1 MeV. And we're also interested in masses of these dark matter, the sterile neutrinos, which are also very tiny, of the order of less than 10 keV. So there's 2.5 keV, there's 4 keV, there's 7.1 keV, and so on. And then just by how I described this, if you are lying on this black line, you end up satisfying the relic density of the universe. You can get this by solving the Boltzmann equation in the early universe. And then for these contributions, you can actually calculate what are the contributions to delta ineffective at the BBN era and the CMB era. So for example, this shaded blue region shows you the region where the contribution to BBN is more than of the order of 50%. And this shows where the contribution to CMB is again of the order of 90%. If you go to lower and lower couplings, the contributions become smaller. Interesting thing to see is that each of these curves have a minima. This happens because for a given mass of the sterile neutrino dark matter, if you come very close to, if the mass of phi comes very close to the mass of the sterile neutrino dark matter, you end up being suppressed by phase space arguments. As a result, you need more and more larger values of the coupling to have the same amount of dark matter. Now, because of this minima, you can see that each of these minima corresponds to certain values of delta ineffective as well. So this minima would again correspond to some line of delta ineffective which intersects with it. What it tells you is that there is an interesting correlation that exists between this minima of the dark matter relic density and the contributions to delta ineffective in the early universe, which you can get. And this is what we try to do. So how do we do this? So for a certain mass of the sterile neutrino, we choose the maximum value of the mixing angle that is allowed. So let's say we look at the 2.5 keV line, then the maximum value of the mixing angle that's allowed should lie somewhere out here. So for this value of the mixing angle, we calculate what the curve should look like if you want to produce the correct amount of dark matter relic in the early universe. And then for that, there exists a corresponding minimum value of delta ineffective at CMB and BBN, which we compute. And this is what the minimum value of delta ineffective and BBN that you get. So therefore, for a given sterile mass and the maximum mixing angle, you can always get a minimum value of delta ineffective. This gives you a target to probe delta ineffective in these models. So you can do it for a real scalar and a complex scalar, and the details are given out here. So these are the constraints that we get. The orange lines shows you the minimum delta ineffective that you can probe for CMB, and then the blue lines show you the minimum delta ineffective that you can probe from BBN. So let's look at the left-hand plot first. The dashed ones are for a complex scalar and the solid ones are for a real scalar. First thing you notice is that you can in principle not probe the delta ineffective at BBN for a very small value of these sterile masses. This happens because when you go to these regions, you end up producing almost negligible amount of phi in the early universe, and then this cannot be probed. But then there's always some minimum value of delta ineffective at CMB that you can probe, because you would have to thermalize the phis after BBN and get them to decay before CMB. So this value is around 0.19%, and this in principle can be probed by upcoming experiments like CMB-S4. Also, as you go to larger and larger values of the masses, what happens is that if you look at this plot, the maximum mixing angle that you're allowed to have becomes smaller. As a result, if the mixing angle becomes smaller, if you remember from our previous arguments, the rate has to go up, which means the lambda values go up. As a result, the values of ineffective also goes up, and that's a reason why this curve increases as you go to larger values of the sterile masses, and eventually comes to a point where this delta ineffective saturates because you end up totally thermalizing the phi. And this again gives you a certain bound on the delta ineffective that you can, the minimum value of delta ineffective that you can probe. You can do a similar study with futuristic bounds on these experiments. So for example, Athena can probe much larger regions of this parameter space. So the bounds on the mixing angles become stronger. And in that case, you can actually get the minimalistic bounds on these delta ineffectives to be larger. And this in principle can actually give additional this can be in principle probed by upcoming experiments like CMB-S4. Finally, in my last slide, what I want to show you is that, remember, this is what I showed was the parameters region of the parameter space where you can find the entire relic density of the universe. And then this was only for values of phi, which was greater than an MeV. As we discussed, you can in principle extend this region to sub-MeV values of phi, and this entire big picture looks like this. This curve nicely extends to this region. We showed this part in the dashed line because the dynamics in these two eras are different. The photon temperature is different in this region, and the photon temperature is different in this region because of electron-positron decoupling. And as a result, they do not map out exactly, but then you see the big picture. And these are the regions in the lambda M5 parameter space where you can satisfy the entire relic density. And these are the corresponding bounds from different experiments. You have meson decays, you have Z decays, you have double beta decay bounds and BBN bounds, and so on. So this concludes my talk. In summary, what I tried to explain out here is that I tried to show a model where essentially if you have a standard model with sterile neutrinos, and then the active neutrinos are allowed to interact very strongly with each other, then this can produce the correct relic density of dark matter in the early universe through these kind of mechanisms. The mediator masses can in principle vary from a few keV to tens of GeVs, as you can see in this plot. This can produce sterile neutrinos, and this in principle can also give you candidates to satisfy your 3.5 keV line if you think that that is due to sterile neutrino decays. Finally, as you can see in US talk, these models can be probed by current and upcoming neutrino experiments and cosmology experiments. So this is a highly testable model. Thank you, and I look forward to your questions.